Hi, everybody, and welcome back. Let's see, today I thought we'd talk about the second derivative, and I should probably give you another little trivia question. So I was hoping somebody can come up with this answer. Over my desk, there is a picture of a creature, and I want to know what is that creature? All right, what exactly is that animal that is up there? Okay, so there's your question. Get back to me with that at some point. So I hope everything went well with the max mins over the last couple days. Any calculus class would start, all right, when you get on the applications after you come up with tangent lines with max and mins is one of the first applications. And really, for those of you who are going into the business world, you will be using a lot of max and min. You'd be looking at a lot of max and min problems because you're looking to maximize profit. You're looking to minimize your costs, all right? And then everything else that goes along with that. Okay, so today, second derivative. All right, let me make sure that my pen is up and working. So any function that we might have is going to have a derivative. As it turns out, equations that aren't functions, all right, are going to have derivatives also, but that's a little more complex, and we'll leave that for Calc 1. Even the derivatives themselves are going to have a derivative to them. So if you think about this following function, if f of x is equal to 2x to the fifth, and you got the other terms there, I'm looking for you to tell me what f prime is, what f prime of x, and what f double prime of x is. So the single prime here means the first derivative. That we kind of already know. If you have two primes in there, it means the second derivative. Now remember, we also had, this was Sir Isaac Newton's notation, Gottfried Leibniz. He used dy over dx to represent the first derivative, and he wrote it as d2y over dx squared for the second derivative. Now, I'm not too worried about that this year, all right, for the basic calculus that we do, but that's something you're going to see next year. All right, let me get rid of all that. So my first derivative. Remember, anytime you're finding the derivative, you got to ask yourself, can I use the power rule or do I have to use the definition? And if you can't use the power rule right away, ask yourself, can you reorganize a problem so you can? In this case, we can use the power rule. We'd have a 10x to the fourth plus 6x minus 4. And at this point, you should be getting pretty quick with these polynomials. Derivative of 6 we know is 0. F double prime of x would be the derivative of the derivative. So 40x to the third, because I'm finding the derivative of that, plus 6, and then the derivative of 4 is going to be 0. So my two derivatives, maybe we'll do this in a highlighter. There's my second derivative. There is my first derivative. And they both have their own purposes. So what do you guys already know the first derivative is good for? Slopes, right? Rates of change. Change of y over the change of x. As it turns out, the second derivative is good for something called concavity. All right. Now, we're not going to look at concavity this year. All right. Again, you'll look at that in a calculus class. If we were there every day this year, we would have looked at some of the concavity. All right. But concavity really has to do with curvature. If I have something going uphill, does it look like that, where it's pretty consistent? Do you actually have it curving up, or do you have it curving down? Those are all three are examples of graphs that are increasing. One has a constant rate of change, constant slope, that's up here. One has a slope that keeps getting steeper and steeper. that's got a positive concavity, as it turns out. And this one, the slopes are getting smaller. They're headed down towards zero. There's a negative concavity there. So it's that second derivative that would allow you to figure out, well, which piece is it really? Again, you don't have to worry about it this year. We're going to use other applications for that. Okay, once you pause this, copy down the problem, and then come up with the first 4 derivatives for me. And once you have those, you can go ahead and play this again and see if your answers match up with my answers. And as you can see, when you're working with polynomials, right, at some point your graph's going to disappear. In fact, if I wanted the 5th derivative, you would tell me 0, and the 6th derivative 0, and the 7th derivative. Now, most of these derivatives beyond the second don't have a whole lot of meaning to them. Right? So very rarely you're going to ask for those, not unless you're just asked about, hey, do you understand the process on finding a derivative? Also keep in mind, we're working with polynomials here. They're easy to work with. When you have y equals the sine of x, and I ask you what's the derivative there, well, that's a little more complex. You're going to have to use the definition, or in a calculus class, you'll learn what the derivative is and you're going to have it memorized. Okay, so let's give some meanings to derivatives, because if you're finding the derivative, which is the slope, all right, we know the slope is the rise over the run, the change of y over the change of x, although this is instantaneous, so it's really dy over dx. We should ask ourselves, what does the y mean and what does the x mean? Right? So one of the easiest types of functions I work with is a position function. Right? Most position functions are going to give to you in terms of s of t. Right? So for example, if s of t equals 10t minus t, right? And I'm just giving you this as information. T is measured in some unit of time. Depending on the problem, T could be seconds, it could be minutes, it could be hours, it could be years, it could be decades, you name it. T could be anything. S of T gives the location of an object, right, in some measure of length, right? So T is some unit. As time goes on in this direction, S of T gives you some height, like a baseball being hit that would follow a path like that. Right? Like a car that is moving or a bike is moving. And what might happen in a car or a bike is maybe you're headed in one direction, another direction, maybe you stop for a while, maybe you keep going, a lot of things could be going on, right? But S of T is measuring something in feet or inches or miles. T could again be in seconds, minutes, hours, right? Depending on the problem. So here's what I want you to think about. S of t, here's what the graph would look like. So this graph here would look something like this. Now, it's possible when it comes back down to the x-axis that it could go through the x-axis, right? It might not go through the x-axis. It doesn't really matter here. I want to talk about what is S of t telling me. So if my t value here, let's say, is measuring the number of hours that have gone by, and my s of t, my y-axis over here, is measuring maybe the number of miles that you've traveled. Our derivative, s prime, all right, s prime of t is the change of y over the change of x. It's the change in miles over the change in hours. It's telling you how many miles per hour. What does that measure? Velocity or speed. Speed and velocity are very closely related, but really velocity is what we're talking about. All you got to do is know what the x is measuring and what the y is measuring and put the y unit over the x unit. And that would always be the units that you should be putting on s prime. So here's what we need to know. If s of t is telling you the position of a function, s prime is giving you the velocity of the function. And we usually don't use s prime, we usually use v of t. As it turns out, the second derivative, the derivative of velocity, is called acceleration. S double prime is acceleration. And we don't usually use S double prime when we're talking about position, velocity, accelerations. We talk about A of t. Right? Position, velocity, acceleration. S, V, and A. The function, the derivative, the second derivative. Velocity. Velocity is usually measured in something like miles per hour. Acceleration, right? Some of you would already know this from maybe a physics class, would be in miles per hour squared. And the position function would have just been in miles. So every time you take the derivative, what you're really doing is picking up a new bottom unit. Okay, does that make sense? If not, maybe take a look back at the slide, all right, and go through that again. All right, let me erase this. Okay, when you have velocity, positive velocity is considered moving forward or moving upwards. Negative velocity is considered moving backwards or down. An example of that, you might consider your house to be a position of 0 and the school, all right, going to school being a positive direction. So the school maybe is 5 miles away from you. That's at a position of 5. If you find out that your S prime, or in other words, your V of t is equal to 40, all right, that would most likely be in like miles per hour. You're telling me you're going 40 miles an hour in a positive direction. If there's nothing here, we know there's a plus. On the way home, if you go the same speed, you would be going a negative 40. And a negative 40, you're going just as fast. The negative just tells us that we are going in a negative direction. A negative velocity means you're going in a negative direction. A positive velocity means you're going in a positive direction. All right, so let's find some position, velocity, and acceleration functions. All right, so today, this is all I want you to do. And then in the next lesson, we'll actually talk about how we can use this to help us solve. Okay, here's my position function. I would like to know velocity, and I would like to know acceleration. So why don't you first take the derivative of the position function. That'll give you velocity. And then once you have the velocity, take the derivative of that for acceleration. And there's what your two functions would be. If the first function is telling me where I am located, the derivative tells me how fast I am traveling. And the third function, the second derivative, tells me whether I want to increase or it gives me the acceleration. Right? And acceleration really is talking about if you want to move in a forward direction or if I want to move in a backwards direction. You might not have noticed this before, but negative 32 is the acceleration for gravity. It has been in a lot of the problems that you've looked at since probably 4th or 5th grade. This is measured in feet per second squared. The other measure for acceleration with gravity is a negative 9.8. That's measured in meters per second squared. These are standards, all right, that you would use in a calculus class. Whoop, I erased it. Let me put that up again. Negative 32 feet per second squared and negative 9.8 meters per second squared. So if a problem was working in feet, that's what you'd use if gravity was playing on it, like somebody throwing a ball in the air. And if a problem was dealing with meters, that's the unit that you would use. Again, if gravity had come into play. There is a decimal here, it's 9.8. Now, when you were younger, they actually took this 9.8 and they rounded it to 10, and negative 10 was in there, although it was really the derivative here. Like up in negative 32, you usually saw minus 16 in the problem because it's before you found acceleration, and half of the 10 down here usually saw a 5. Sometimes you saw negative 9 at 4.9. Okay, now that's not as important to you right now, all right? But it's always been in your problems that you've looked at. Okay, how about this one? I'm looking for my two functions. It's not exactly set up to use the power rule yet. So what can I do? I can rewrite this. So the first thing I would do is I would take your S of t, and why don't you FOIL these terms together for me? I got a minus 4t squared minus t, or minus 1t minus 14. Take away, and in this last term, I also can't take the derivative yet, so I'm going to bring my t to the 4th up above and make this 5t to the negative 4. All right, so now it's in a form where I can take the derivative. I can't leave it in the bottom if I want the derivative. Okay, velocity, acceleration. Take a minute, do your two derivatives for me. Again, you might want to pause this because I'm going to go ahead and put up my answers. And with the velocity, this last term you would want to rewrite as 20 over t to the 5th. I was just running out of room. And in the acceleration, you'd want this as to be 100 over, why am I putting an x there? T to the 6th. Right, so get rid of those negative exponents. Right, so we're just combining skills, right? Things that we've talked about in the last couple of weeks, and now adding it into coming up with a second derivative and third derivative, but giving this a meaning, all right? Position, velocity, acceleration. Now, in this last one that I have for you, again, your job will be to clean this up. Right now, you cannot use the power rule. You can't just take the derivative of the top and then start to take the derivative of the bottom. That's not how calculus works. All right. What I can do is I can rewrite this as t squared over the cube root of t would be t to the 1/3. See, what's the rule for dividing like terms? We leave the term and we subtract the exponents. So 2 minus 1/3 would be 1 2/3, which means this is t to the 5/3. And now's when you can find your derivative for me. b of t, I'm going to put a 1 in front. 1 times 5/3 would be 5/3. T to the, if I subtract 1 from here, subtracting 1, that's the same thing as 3/3. So 5/3 minus 3/3 would give me 2/3. For the acceleration formula, A of t, I've got 5/3 times 2/3, which would be 10/9. When I subtract 1 from 2/3, I get t to the negative 1/3. And when I rewrite this, now I don't write this as two fractions. I just, either the t is with the top, or to make it a positive, I move it down to the bottom. So I've got 10/9 t to the 1/3. Then I only have to work with one fraction. Okay, so that's today's. I want you to find the second second derivatives also, first derivative, second derivative, but we also want to start giving this meanings, all right? There's no point on using the second derivative if you can't actually use it, and there's no point on finding the first derivative either if you can't go ahead and use it. Okay, good luck. Answer that trivia question. Your homework is on a worksheet, all right? And I'll talk to you again next time.